Hello aspirants, welcome to Magic World of Physics. In this video, we're going to discuss about some questions from solid state physics which is asked in various exams like GATE, Barc, Just, Differ. Hope this video will be helpful for your coming Barc exam 2026. Without any further delay, let's get started. The first question is, what is the second nearest neighbor distance in an FCC whose conventional unit cell parameter is A? In FCC lattice with a conventional parameter A, the atoms are located at the corners and the center of each face. The nearest neighbor are the face and is relative to a corner atom with a distance of A by root 2. The second nearest neighbors are the atoms along the edges at a distance of A from the corner atom. So here the answer is option C. Next question is, the distance between the adjacent atomic plates in CaCO3 is 0.3 nanometer. The smallest angle of Bragg scattering for 0.03 nanometer X-ray is. Here it is given that the interatomic distance d is equal to 0.3 nanometer. The wavelength of the X-ray lambda is equal to 0.03 nanometer. So by the Bragg's law, n lambda is equal to 2d sin theta. Here n is taken as 1. That is sin theta is equal to lambda by 2d. That is sin theta is equal to 0.03 nanometer divided by 2 into 0.3 nanometer, and this is equal to 1 by 20. Therefore, theta is equal to sin inverse of 1 by 20, and this is equal to sin inverse of 0.05. Therefore, theta is equal to 2.86 and this is equal to 2.9 degree. So here the answer is option A. Next question is, for a NaCl crystal, the cell edge A is equal to 0.563 nanometer. The smallest angle at which the Bragg's reflection can occur corresponds to a set of planes whose indices are. We know that D is equal to A divided by square root over h square plus k square plus L square for a cubic system. We know that HKL are the Miller indices. And by Bragg's law, n lambda is equal to 2d sin theta. That is, sin theta is equal to n lambda by 2d. For minimum value of theta, we know that d must be maximum. That means for maximum d, square root over h square plus k square plus L square value will be minimum. So among the given option, only 100 show minimum square root over h square plus k square plus L square value. That means which has given the smallest theta. So here the answer is option A. Next question is, silicon has diamond structure with unit cell edge A is equal to 0.563 nanometer. The interatomic separation is dash. Here we need to find the value of interatomic separation, that is D, and it is given that A is equal to 0.543 nanometer. We know that D is equal to 2R, and for the diamond it has a FCC structure, therefore 4R is equal to A root 2. That is, 2R is equal to A root 2 by 2, and this is equal to A into 1.414 by 2, and this is equal to 0.707 into 0.543, and this is equal to 0.383 nanometer, and we can write it as this is equal to 2R. That means this is equal to D. So here the answer is option C. The next question is, if the ionic radii of Mn and S are 0.80 and 0.184 nanometer respectively, the structure of MnS will be. So let the cation radius be R plus and anion radius be R minus. And here it is given that the ionic radius of Mn, that is the cation, so here R plus is equal to 0.80 nanometer, and the ionic radius of S, and it is the anion, therefore R minus is equal to 0.184 nanometer. Therefore, R plus by R minus is equal to 0.80 divided by 0.184, and this is approximately equal to 0.435. If the ratio is between 0.225 and 0.414, then the coordination number is 4. It is tetrahedral like zinc blende. If the ratio is between 0.414 and 0.732, the coordination number is 6. It is octahedral like NaCl type. If the ratio is between 0.732 and 1, then the coordination number is 8. That means it is cubic like CaCl type, that is cesium chloride. So here the calculated ratio is 0.435, which falls under the range of 0.414 to 0.732. That means here the coordination number is 6, and the structure is of NaCl type. That means the face-centered cubic arrays of anions and cations in the tetrahedral voids. So here the answer is NaCl type. Next question is, a crystal belongs to a face-centered cubic lattice with 4 atoms in the unit cell. The size of the crystal is 1 centimeter and its unit cell dimension is 1 nanometer. F is the scattering factor of the atom. The number of atoms in the crystal is dash, and the structural factors for 010 and 200 reflections respectively are. Here A is equal to 1 nanometer and this is equal to 1 into 10 power minus 10 meter, and the size of crystal is 1 centimeter. Therefore, the number of unit cells in the crystal is 1 centimeter into 1 centimeter into 1 centimeter divided by 10 raised to minus 10 meter into 10 raised to minus 9 meter into 10 raised to minus 10 meter. So this is equal to 10 power minus 2 into 10 power minus 2 into 10 power minus 2 meter cube divided by 10 raised to minus 9 10 raised to minus 9 into 10 raised to minus 9 meter cube, and this is equal to 10 power minus 6 divided by 10 power minus 27, and this is equal to 10 power 21. So the number of atoms in the crystal is equal to the number of atoms per unit cell into the number of unit cell. That means this is equal to the 4 into 10 power 21 atoms. So here the answer is option B. For FCC lattice, it is having 4 atoms at 000, half 0 half, half half 0, 0 half half position, and it is given by F is equal to F into 1 plus e raised to pi I into h plus L plus e raised to pi I into h plus k plus e raised to pi I into k plus L. So here for 0 1 0 we can write f is equal to f into 1 plus e raised to pi I into 0 plus 0 plus e raised to pi I into 0 plus 1 plus e raised to pi I into 1 plus 0. So this is equal to f into 1 plus e raised to 0 plus e raised to pi I plus e raised to pi I, and this is equal to f into 1 plus 1 minus 1 minus 1, and this is equal to 0. And for 200 we can write f is equal to f into 1 plus e raised to pi I 2 plus 0 plus e raised to pi I 0 plus 0 plus e raised to pi I 0 plus 2, and this is equal to f into 1 plus e raised to 2 pi I plus e raised to 0 pi I plus e raised to 2 pi I. This is equal to f into 1 plus 1 plus 1 plus 1, and this is equal to 4f. So here the answer is option B. Next question is, the C by A ratio for an ideal hexagonal closed packed structure is. The C by A ratio is typically around 1.633, that is approximately equal to square root over 8 by 3 for a CCP structure. In a CCP structure, the atoms are arranged in a repeating pattern of closely packed layers, with each layer consisting of atoms arranged in a hexagonal pattern. So here the answer is option D. The next question is, in the crystallographic notations, the vector OP in the cubic cell shown in the figure is. So here the vector OP is A and A by 2. So taking the coefficient, we can write it as 1, 1, 1 by 2. Multiplying it by 2, we can write it as 2, 2, 1. So here the answer is option A. Next question is, for a closed packed BCC structure of a hard sphere, the lattice constant A is related to the sphere radius R as. So for BCC, the atoms lie at the corners as well as the body centers of the cube. So here 4R is equal to A root 3. That is A is equal to 4R by root 3. So here the answer is option A. The next question is, which of the following axes of rotational symmetry is not permissible in the single crystal? So here cos phi n is equal to n by 2, where n is the integer. So the number of the possible fold axes n is equal to 360 divided by phi n. And we know that the value of cos phi is between 0 and 1. So the possible value of phi n is 360, 180, 120, 90 and 60. So the number of fold axes are 1, 2, 3, 4 and 6. That is, here phi is not possible. That means 5-fold axis is not possible here. So here the answer is option D. Consider the atomic packing factor APF of the following crystal structure, that is the simple cubic, body-centered cubic, face-centered cubic, diamond, hexagonal close packed. Which two of the above structures have the equal APF? The atomic packing factor of simple cubic is 0.52, BCC is 0.68, FCC is 0.74, diamond is 0.34, hexagonal close packed is 0.74. So here FCC and HCP has the same APF. So here the answer is option D. Next question is, the primitive translation vectors of the FCC lattice are A1 is equal to A by 2 into J plus K, A2 is equal to A by 2 into I plus K, A3 is equal to A by 2 into I plus J. So the first part question is, the primitive translation vectors of FCC reciprocal lattice are dash, and the second part is, the volume of the primitive cell of FCC reciprocal lattice is dash. So here we know that the primitive translation vectors of the reciprocal lattice are b1 is equal to 2 pi into a2 cross a3 divided by a1 dot a2 cross a3, b2 is equal to 2 pi into a3 cross a1 divided by a1 dot a2 cross a3, b3 is equal to 2 pi into a1 cross a2 divided by a1 dot a2 cross a3. So solving these values, we can get b1 is equal to pi by a into minus I cap plus j cap plus k cap, b2 is equal to pi by a into I minus j plus k, and b3 is equal to pi by a into I plus j minus k. So here the answer is option B. Let's move to the second part. So here we need to find the volume of the reciprocal lattice. The volume of the reciprocal lattice V star is equal to 2 pi the whole cube divided by V. So here V is equal to A1 dot A2 cross A3. We know A2 cross A3 is equal to A by 2 into I plus J cross A by 2 into I plus J. That is equal to IJK A by 2 0 A by 2 A by 2 A by 2 0, and this is equal to I into 0 minus A square by 4 minus J cap into 0 minus A square by 4 plus K cap into A square by 4 minus 0, and this is equal to minus A square by 4 I cap plus A square by 4 J cap plus A square by 4 K cap. Therefore, V is equal to A1 dot A2 cross A3, and this is equal to A by 2 into J plus K into A minus A square by 4 into I cap plus A square by 4 into J cap plus A square by 4 into K cap, and this is equal to A cube by 8 plus 8 cube by 8, and this is equal to 2A cube by 8, and this is equal to A cube by 4. So we can write V star is equal to 2 pi the whole cube divided by a cube by 4, and this is equal to 8 pi cube by a cube into 4, that is equal to 32 pi cube by a cube, and this is equal to 4 into 2 pi by a the whole cube. This is the answer. Next question is, what is the ratio of the intercept on the 3 axis by 1, 3 bar, 2 planes in the simple cubic lattice? So here let PQR be the intercept on the XYZ axis. Therefore P is to Q is to R is equal to A by H is to B by K is to C by L. Therefore we can write P is to Q is to R is equal to A by 1 is to B by minus 3 is to C by 2. Taking LCM and multiplying it with 6, we can write it as 6 is to 2 is to 3. Therefore, the ratio of the intercept on the 3 axis is 6 is to 2 is to 3. The next question is, consider X-ray diffraction from a crystal with FCC lattice. The lattice plane on which there is no diffraction peak is dash. The selection rule for FCC lattice is, it shows the X-ray diffraction peak only when the Miller indices are purely even or purely odd. So in the option 212, these indices are a mixture of even numbers and odd numbers, so there is no diffraction peak here. In option B, 111, all indices are odd, so a peak is observed here. And in option C, 200, all indices are even, a peak is observed here. And in option D, 311, all indices are odd, a peak is also observed here. So here the peak is not observed in option A. So here the answer is option A. Next question is, the number of different Bravais lattices possible in 2 dimension is? So the number of different Bravais lattices possible in 2 dimension is 5. They are oblique, that means A not equal to B, and gamma not equal to 90. The second is square. Here A equal to B and gamma is equal to 90. Third is the primitive rectangle. Here A not equal to B and gamma is equal to 90 degree. And fourth is non-primitive rectangular. Here A not equal to B but gamma equal to 90 degree. And the fifth is the hexagonal. Here A equal to B and gamma equal to 120. So here the answer is option C. The next question is, an electron of mass m moves in a square lattice spacing A. Assume that the nearly free electron approximation holds good. If there are 2 electrons per side, then which of the following is correct? So here the answer is the system behaves as an insulator because in a square lattice the first belonging zone is a square. According to the nearly free electron approximation, the energy gaps open up at the boundaries of the zone. The number of available energy states within the first belonging zone is exactly 2 per unit cell. With 2 electrons per site, all the available state in the first belonging zone are completely filled. So the energy gap prevents the movement of electrons to the higher energy state. So there is no free electrons here. That means the system behaves as a insulator here. So here the answer is the system behaves as a insulator. Next question is the real space primitive lattice vectors are a1 is equal to ax cap, a2 is equal to a by 2 into x cap plus root 3 y cap. The reciprocal space unit vectors b1 and b2 for this lattice are V is equal to A1 dot A2 cross A3. A2 cross A3 is equal to A by 2 into x cap plus root 3 y cap cross A3. A2 cross A3 is equal to A by 2 into x cap cross A3 plus root 3 y cap cross A3. So that A2 cross A3 is equal to A by 2 into minus y cap plus root 3 into x cap. And here V is equal to ax cap dot a by 2 into root 3 x cap minus y cap. So this is equal to a square by 2 into root 3 into x cap dot x cap minus x cap dot y cap. So that V is equal to a square into root 3 by 2. That is V is equal to a square root 3 by 2. Here b1 is equal to 2 pi into a2 cross a3 by v. That is, this is equal to 2 pi into a by 2 into root 3 x cap minus y cap divided by a square root 3 by 2. That is equal to 2 pi a into root 3 x cap minus y cap divided by a square into root 3. And this is equal to 2 pi divided by a root 3 into root 3 x cap minus y cap. And this is equal to 2 pi a into x cap minus 1 by root 3 y cap. And here b2 is equal to 2 pi into a3 cross a1 by v. We know a3 cross a1 is equal to a3 cross a into x cap. And this is equal to a into a3 cross x cap. That is a3 cross a1 is equal to a into y cap. Therefore b2 is equal to 2 pi a into y cap divided by a square root 3 by 2. This is equal to 2 pi 2a y cap divided by a square root 3. Therefore b2 is equal to 4 pi divided by a root 3 y cap. Therefore, here the answer is 2 pi by a into x cap minus 1 by root 3 y cap and 4 pi by a root 3 y cap. The next question is, for the given unit cell of a two-dimensional square lattice, which option lists all the primitive cells? So primitive cell is a unit cell that contains exactly one lattice point. And they should follow some condition. The first condition is the arrangement can be built up the whole crystal without overlaps and gaps. The second is there is no further partition of the unit cell that could itself be used as a unit cell. So here the figure 1, figure 2, figure 3 and figure 4 satisfies these conditions. So here the answer is option C. This is the end of this video. Thanks for watching this channel.